this video, I'm going to give you two examples of improper integrals. We'll figure out if they converge or diverge, and specifically I'm going to do that by just evaluating them. Another technique you can use for improper integrals is comparison, but I won't talk about that here. We'll just talk about evaluation. Okay, so really quickly, what is an improper integral? An improper integral is any kind of an integral that involves infinity somehow. That could happen in two ways. Either there's infinity like this, or infinity like this. That's a little vague, and I'll explain what I mean by that in detail. But with this integral in particular, which is from e to infinity of some function, there's definitely an infinity like this involved just because of this upper bound. The fact that the upper bound is infinity immediately tells me that this integral is improper. Okay. Now the question given any improper integral is, does it converge or diverge? Because an improper integral involves infinity in some capacity, there's a chance that the value of this thing doesn't really make sense, or rather, there's a chance that this thing is just infinity or something like that. So the main question we're interested in is exactly, does it converge or diverge? Okay, so what's the point? How do you deal with something like this? The only difference between an improper integral and a regular integral is really, in practice, you just write it as a limit. For example, this one, we look at it and we say, okay, well, it's ridiculous to have an infinity here. That doesn't make any sense. I don't know what that means. So instead of integrating from e to infinity, I'll just integrate from e to some finite number. That makes sense. And then I'll take a limit. Okay. Now, one thing to ask yourself every time you get an improper integral is why is the integral improper? The reason why this is important is because if the integral is improper for multiple reasons, you have to split it up into multiple pieces. In this case, this doesn't happen. It's definitely improper because of the infinity. There's no other reason why it's improper. The other kind of bad thing that could happen is if you divide by 0 at some point. That would be a 1 over 0. That would be involving infinity in this capacity. But that doesn't happen because x is never 0, since we're integrating from e to infinity. Log of x is never 0 either because we're starting at e. Log of e is 1, and then from then on out it's positive. So we don't have to worry about that here. So for this example, the only reason why this is improper is because of the infinity. Okay? So what do? You just write it as a limit. In other words, you just turn the improper integral into a limit of proper integrals. In this case, the way that I would do that is I would start with what we're given. And I say, this is garbage, doesn't make sense. I only know how to integrate from a finite number to a finite number. So in place of the infinity here, I'll just put a variable. I'll call this capital R, or whatever you want to call it. This makes sense if R is a finite number. And then this is just the limit as R goes to infinity of this integral. Now from here on out, this expression will evaluate as always, and then we just have a limit to take at the end, and we'll be done. Now, how would I evaluate this integral? I would probably do a substitution. I identify the composition of functions here. It's like blah, 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 something cubed. That's a little ugly looking. And I recognize that if I call u log of x, I've got a 1 over x dx sitting out front. So I would do a substitution where I say I'm going to let u be log of x, du is 1 over x dx. Then I have to change everything here, including the bounds. The bounds, when x is e, log of e is 1. When x is r, u is log of r. That's a little weird, that's okay. The integrand turns into 1 over u cubed du. And then this is a power rule problem. This is u to the negative 3. So the antiderivative is no problem. Power rule says bump up the exponent by 1 to negative 2, which is 1 over u squared. And then divide by the new exponent, which is negative 2. So there would be a negative 2 down here. The negative sign I could put upstairs. And then I'll evaluate that at log of r and 1. Okay? So when you plug in log of r here, this will be a negative 1 over 2 log of r quantity squared minus this expression evaluated when u is 1, which is negative 1/2. So this is plus 1/2. And now this is a limit problem. As r goes to infinity, 1/2 is constant. This term, the log of r grows to infinity, so sending r to infinity sends this expression to 0. And we're left with 1/2. Okay. This tells us a couple things. First of all, the fact that we got a finite number by doing this process implies that the integral converges to a finite number. And in fact, it converges to 1/2. That's the value of this improper integral. Anyway, I just asked if it converged or diverged, so we could finish off the problem by saying, since 1/2 is a finite number, the integral converges. Okay, one more example. We'll deal with it in pretty much the same way. The only difference with this improper integral is that there's no longer an infinity in the bound. So in other words, there's no infinity in this direction. The infinity that's involved is in the vertical direction. Roughly what's happening there is near negative 1, I can already see that if I try to plug in negative 1 for x, I'll be dividing by 0. That's indicating that the function has a vertical asymptote at 0. Sorry, at negative 1. What that means is there's a vertical infinity, and so there's a chance that we accumulate infinite mass in the computation of this integral. But again, I'll proceed just like I did before. Why is this integral improper? The reason this time is because the function blows up at negative 1. The integrand explodes at negative 1. In other words, there's a vertical asymptote, and that's bad news. Okay. Now, is there any other reason why it's improper? I would say no. We're not going off to infinity, and the only way for the denominator to be 0 here is when x is -1. So this is the only reason why this is improper. Okay, so like I said, we'll do pretty much the exact same thing. I just wanted to draw a quick picture to give you an idea of one little thing I'm going to do, which is the function probably looks something like this on the interval -1 to 0. As you approach -1, numbers get bigger and bigger and bigger, and so here's this vertical asymptote. Sort of. And the integral that we're trying to compute is roughly the area under this curve. Now, when we rewrite this as a limit, like we did in the previous example, the only difference is, well, last time I changed the upper bound, but this time the trouble spot is at -1. So this is what I'm going to change. I'm going to call this a variable r. Zero's fine, so I'll leave it alone. And then I'll take a limit as r approaches. Now I'm not integrating off to infinity. What I want to do is send r closer and closer to -1. But when I think about this limiting process, what we're doing here is, because this is the area that we care about, these integrals are computing areas specifically like this. And I take r closer and closer and closer to -1. But I do so only from the right-hand side. That is, I don't care what happens on the left-hand side, and sometimes it might not even make sense to do that, depending on what kind of integral you have. So when I write this limit here, I'm actually going to specify that this is a limit from the right. R is approaching -1 specifically only from the right, and I don't care about the two-sided limit or the left-handed limit at all. Other than that, nothing's different. We proceed just as we did before. We have an integral to do. We'll go from there. Also, just like before, this can be integrated with a u substitution. So I would say, in this case, let me let u be x plus 1. du is dx. How does this transform? Whoop, -1 from the right. The bounds change as when x is r, u is r plus 1. When x is 0, u is 1. The integrand becomes 1 over u to the 3/2. dx is du. And so here we are. Just like before, this is a power rule problem. I can think about this as being -u to the -3/2. So power rule says bump the exponent up by 1. If I increase -3/2 by 1, -3/2 plus 1 is -1/2. So the antiderivative will be u to the -1/2. Increase the power to -1/2, divide by the new exponent, evaluate at 1 in r plus 1, and then take a limit as r goes to -1 from the right. Okay. I'll continue this down here. When you plug in 1 here, 1 to the -1/2 is 1. So this is like 1 over -1/2, which is -2. Minus, plug in r plus 1, minus a -2 is like plus 2 over r plus 1 to the negative 1/2 is like the square root of r plus 1 in the denominator. Okay. Here's another indication of why we do have to specify that this is a limit being taken from the right, because this expression would not make sense if I didn't have the plus sign here. In other words, if you tried taking the limit of this as r goes to -1 from the left, something bad's going to happen because you'll be plugging in numbers more negative than -1. So like -1.1. But if you do that, you'll be taking the square root of a negative number. That's bad. So that's another reason, or another way you can see why we do only care about the one-sided limits, rather. Okay, in any case, as r goes to -1 from the right, this expression is going to 0 in the denominator, which means this is going to blow up to infinity. So the limit of this expression is infinity. And what that tells us is that when we try computing the area under this curve and I send these integrals closer and closer and closer to -1, you accumulate infinite area. Therefore, since we got infinity here, this integral diverges. Done.